Okay, welcome back. So last time we have proved some estimates on the rescaled equation and determined the blow-up rate of the curvature. We also got an upper bound on the scalar curvature. And then I pointed out that in order to get the lower bound on the scalar curvature, we have to control the injectivity radius of the rescaled matrix. And to do that, let me just briefly recall what the injectivity rate is, injectivity radius, I should say, and how to think about it. A good reference for this is the book by Cheever and Evin. But of course you find a discussion of injectivity radius and Meyer's theorem in many other books. So control of the injectivity radius. So let us recall a definition given a point P in the manifold, the injectivity radius I of P at P is the largest radius R such that the exponential map is a diffeomorphism onto ball of radius r around P. So now how could the exponential map go wrong? What could go wrong? Well, the exponential map around a point is creating these spheres such that the geodesics are orthonormal to these spheres of radius r from this point P. Now, the only way the exponential map can become no longer a diffeomorphism is that either another geodesic reaches this point here, so yeah, maybe draw this in a slightly larger picture. Suppose it goes wrong here. If this, we have two geodesics reaching the same point, then you have, turns out you have a whole family of geodesics joining these 2 points P and Q. So, so X at P can cease to be a diffeomorphism either if there exists Q such that there is a family of geodesics between P and Q. I'm reporting facts now, and a Jacobi field in between joining P and Q on this, along this geodesic, along this geodesic from P to Q, i.e. some y with y at P equals y at Q equals 0, and turns out this variation of geodesics leads to an ODE of second order for this vector field, for this variation vector field. Namely, you get the s squared of yi is Riemann tensor jkl times gamma dot j times yk times gamma dot l. We have the so-called Jacobi equation for vector field. Right, so one way for the exponential map to no longer be a diffeomorphism is when these two vertical geodesics in the normal coordinate system all of a sudden no longer give you the diffeomorphism, but they meet. Now, the one thing that could also happen is that it just keeps going on the other side. So in other words, that this angle here between is 180 degrees. And then it turns out this is the situation in the cylinder where the geodesic just keeps going around and comes back to itself. Or there is a geodesic there's a geodesic, closed geodesic, which goes from P to Q back to P. And this has then the length of this gamma, which we then twice the distance between Q and Q. These are the two, this is just a fact on the characterization of the injectivity radius. If you have two such points, P and Q, with a Jacobi field in between, you would call this conjugate points. So this is also a brief description about this conjugate points. Now, how can we rule this out using our how can you rule this out? So this corresponds, maybe I should draw the picture. I've drawn it, yeah, I've drawn this picture, and here, maybe I should draw this picture here. This is, of course, the picture with the cylinder, right? Where you have the point P here and point Q there, and you have the geodesic going around. There's no Jacobi field here, because it's flat space, so this equation obviously would not have solutions which satisfy these two boundary conditions at P and Q, but you have nevertheless the exponential map ceasing to be a diffeomorphism up here, because you come to the same point from two different sides, and this gives you this closed geodesic that meets up at Q. So how can we rule this out using the conditions that we've already proved on our evolving metric? Now, the upshot is a famous lemma which was first proved by Wilhelm Klingenberg. This lemma says that if you are on a closed, if on a closed, simply connected manifold, the sectional curvatures sigma ij of the Riemannian metric satisfy that they are between 1/4 some positive number, strictly inequality, and k, or some constant k greater than 0, then for each p in the manifold, we get that the injectivity radius at p is bigger than pi times k to the minus 1/2. And this is, of course, the number that you would get on the sphere of sectional curvature 1, because then you go distance pi from the North Pole to the South Pole. Now, the proof ideas, don't give a comment. Proof ideas is that note by Meyer's theorem, and the lower bound that you get on the Ricci curvature. You see, if each sectional curvature is bigger than 1/4 times k, then the sectional curve, the Ricci curvature, which is n-1 times this guy, so you get n-1 divided by 4 times k times gij. You get that the diameter, that all geodesics, but in particular the diameter, I should say all geodesics of length more than k to the minus 1/2 times pi over 2 have conjugate forms. I get this right? No, it's the inverse, it's twice. I have to take the k to the minus 1/2, and the inverse of the square is 2 times pi, right? So this means it cannot, so this essentially roots out the minimizing curve going around twice. And the other point is, of course, if you have the other upper bound, also the Jacobi equation would say something like, if you integrate it after multiplying with y, would give you something like integral over gamma of ddSy squared. ds would be less than k times integral y squared ds over gamma, which would mean that the first eigenvalue of gamma would be less than first eigenvalue of ds squared is less than k on gamma. But this would mean that the length of gamma would have to be bigger than pi k to the minus 1/2. Right, so this these are sort of the principal ideas why you need on the one hand this inequality and why you need on the other hand that inequality. But as I said, a good reference with precise proofs rather than just ideas is in the book of Chiga and Eppen. What we are going to use is exactly this lemma of Klingenberg as stated. I could have just stated it, but I wanted to make it plausible. So, in our case, the pinching condition of Klingenberg, the so-called quarter pinching condition, is true if we have time large enough, because the minimum and maximum of the scalar curvature approach each other, and the other components of the Riemann tensor, V and W, are getting small compared to the scalar curvature. So in our case, for t close to t max, we have that the v squared plus w squared is less than epsilon times r squared because of our pinching condition. In view of pinching. Assumption. And since this is scaling invariant, this is of course also true for the rescaled metric. But this means in particular that our sectional curvatures are between sectional curvature, how big are they? They compare to the scalar curvature. They are like 1 over n times n minus 1 times plus a little bit times r max and bigger than 1 over n minus 1 minus epsilon. Very also used that R min is tilde R min divided by R max. Okay. So we have certainly the much weaker assumption of Klingenberg is certainly satisfied in our case with k equals to R max. So Klingenberg condition is satisfied for k. Okay. So this means that certainly our injectivity radius is bigger than pi, times R max to the minus 1. And this now allows us to argue with what we know in the normal coordinate system. Now, this was assuming Klingenberg was assuming the manifold is simply connected. So we have to apply Klingenberg's result in the universal cover of our manifold. So using this, we get in the universal cover n hat of n, we therefore, so this is true if simply connected. Now, we don't want to assume our manifold is simply connected, but the universal cover of M is simply connected. We therefore can estimate that the volume of a ball of size injectivity radius around P is bigger than some constant times what you get from this curvature. So you get R max to the minus n over 2. So therefore also you get that the volume of the universal cover is at least that big. So we have this lower bound on the volume, and now since the maximum of the curvature is comparable to the minimum of the curvature, this would give us the desired bound on the minimum of the scalar curvature if our manifold is simply connected. So if we're simply connected, we are done. So we're done if Mn is simply connected, since V tilde is equal to 1 and R min bigger than 1/2 R max. Okay? So the problem is the manifold might not be simply connected. Now, if it's not, and think of these examples that I gave you about the length spaces. In those cases, they were simply connected, but sort of the order of the group determined how big the volume is, how much smaller the volume is. So, in those cases, we would be fine because we would just have to divide our estimate by an extra factor coming from the order of the discrete isometry group. The problem is, we need to know that the fundamental group is finite, so that we don't have to divide by an infinite order. And so in other words, we have to make sure that the universal cover doesn't have infinitely many layers, meaning we have to show that the fundamental group is finite. So similarly, we are done if the fundamental group phi 1 of Mn is finite. Say order of phi 1 Mn equals alpha, then so this would be the ball inside the fundamental group, then the volume of the ball injectivity radius around P of P inside the original manifold would be bigger than C over alpha times R max minus N over 2. Okay. So it remains to show that the fundamental group is finite. But this is well known because in our case the Ricci curvature is strictly positive, and it's well known that if the Ricci curvature is positive, then the fundamental group is finite. So, once more, we make use of the positive curvature to deal with this last remaining problem. So this is a well-known proposition. If on a compact manifold we have that the Ricci tensor is bigger than some kappa, Gij kappa bigger than 0, then pi 1 over Mn is fine. And the proof idea, just the idea, is of course Meyer's theorem. By Meyer's theorem, any stable geodesic, let's write the n minus 1 to make the constants nicer. Any stable geodesic is length less than pi k to the minus 1/2 times 2, because each half is then stable. And so this would be a closed stable geodesic, has a uniform upper bound on its length. So if you now had, if there are infinitely many, many homotopy classes, omega I in pi 1 of Mn, you can find a minimizing geodesic in each one of them. Find gamma I minimizing geodesic, for example, in the torus, you can find for each number of loops around one of the S1s, you can find, of course, such a minimizing geodesic. But in the torus, they get longer and longer, whereas here, we know they all satisfy that the length of gamma I is uniformly bounded by 2 pi k up to the minus 1/2. So since you have this uniform length on these geodesics, you have the geodesic equation, it's not so hard to see, use Arzel's coding to get this convergent subsequence. Can be smoothly to some closed geodesic again. But because of this smooth convergence, they all have to be in the same homotopy class eventually. So they have to be eventually in the same homotopy class. And this is a contradiction because we assume that they are all in different homotopy classes. Okay, so that was a sketch of this proposition. So we have a finite, because of our pinching assumptions and positive scalar curvature, we know that eventually the Ricci curvature is positive. So the manifold must have had finite fundamental group. Therefore, we get our lower bound on the volume, and therefore we got our lower bound on the scalar curvature. So we have now a corollary that sums up all this information. So there exist constants C1 and C2, depending on our initial data and our pinching assumption, such that we have the minimum of the Huisken. This is of course less than R tilde, which is less than the maximum of the scalar curvature, and this is less than C1 to the minus 1 second. And on the other hand, we get from this that our factor psi of t is both bounded above by a constant t max over t and bounded below by because again this is related to the volume, and we have now seen that the volume with Meyer's theorem gives us the upper bound, and with Klingenberg's lemma we get the volume comparison in the other direction, gives us this bound. So this means in particular that if we had done this other scaling method, the scaling method that I mentioned, yes, we are on the right track. So, but you would have had, of course, the same problems, and you would have needed to use Klingenberg's lemma to get this conclusion also if you had made the ansatz that psi of t is equal to this fact. Okay, now we have the minimum of the scalar curvature bounded from below. Let's see how that affects our estimates, and let's get exponential convergence. Okay. Right. So in the next step, we conclude now that the integral of the that the new maximum time interval is infinite. You get solution on all time. And the proof is quite simple, because when you take the integral from 0 to t max of the maximum of the average of the scalar curvature, then this is of course bigger than the minimum of the scalar curvature. And since the minimum is bounded from below by so this is infinite, since the minimum of the scalar curvature was bounded below by some constant divided by T max minus T. So you get this logarithmic blow up. So this is infinite. But on the other hand, this integral, by just change of variables, this is the same as the integral to T tilde max of R tilde of T of tau d tau, since since the tau by dt, the change of variables was just psi. So the change of variables of time in the curvature is just opposite, so it cancels out, and you get the same integral. But now we know that the curvature is bounded from above. So this is estimated by R tilde max times T tilde max. And this is bounded. This is a bounded number. And therefore T tilde max must be infinite. Okay, so we have an infinite time interval on which our evolution exists. The other, let's translate our pinching conditions. Also notice that V tilde squared plus W tilde squared by assumption and scaling invariance, this is equal to this, as we observed before. By assumption, this was less than the constant times R to the minus delta. But R to the minus delta is now, we know that this is less than R minimum to the minus delta. And the minimum blows up by 1 over T max. So with the inverse, we get that this is less than T max minus T to the delta. So this goes down like this, at this rate. But on the other hand, we have here this relation between tau and t, and we have the estimate of psi. Psi is like 1 over the remaining time. So if we integrate this, notice that T max minus T, just by integrating this 1 over T thing, you get the logarithm, and then inverting that, you get that T max minus T is less than, this is essentially because psi satisfies this estimate. Psi is order 1 over T max minus T. You get that T max minus T is less than T max times e to the minus tau over some constant. So the power decay in the remaining time, because the new time variable essentially is a logarithm, this decay in a power of the remaining time translates into exponential decay in the tau variable. So putting this together and noticing that R tilde is bounded from above by a fixed constant, we get that v tilde squared plus w tilde squared is bounded by some constant times e to the minus tau delta over c. So we get some very small exponential decay in tau in our tilde variable. Okay, so now we have the trace, we've translated our pinching assumption after rescaling using our estimates. We've translated this into exponential decay of the trace-free part of the Ricci tensor and of exponential decay of the Y tensor. So now all we need is to transfer this to the higher order derivatives, and then we get that the whole metric will exponentially converge to a smooth limiting metric. So in the next step, then recall we had this evolution equation ddt of gradient r squared over r plus n times traceless Ricci tensor and we had that this is less than the Laplacian of this whole thing. And then we had something left over, which was n times gradient Ricci squared. Remember, this was this lemma where we decomposed the gradient of the Ricci tensor into these irreducible terms, and then we got something extra from the Bochner term in here. And we only had to pay for this by some term n times r times something that involved v squared plus w squared. And we could estimate all that was right on the right-hand side by n times, let's write it like this, r times v squared plus w squared. Yeah, let's write it like this. That's what we proved. Now, how does this change as we go to the rescaled equation? Now, notice another little lemma, how to transfer an evolution equation or inequality that we have proved for the original equation into the rescaled equation. Right? So if a quantity P scales like psi to the alpha, so P tilde equals scales with degree alpha. So P alpha, P tilde is equal to psi to the alpha times P. So for example, the metric scales with degree 1, the curvature scales with degree minus 1, the volume form the scales with degree n over 2, and so on. And satisfies ddt of p less than Laplace p plus q, then you get dt tau of p tilde is less than Laplace tilde of p tilde plus q tilde plus, and then the extra term is alpha, the degree, times 2 over n little r tilde times p tilde. So you get this extra term that comes from the Huisken. You already know this because in the metric, which is of degree 1, you got in the new evolution equation for the metric 1 times 2 over n r tilde times the metric. So this is just a generalization, and it's the same computation. Just do the time derivative of this and insert the time derivative of psi, which is related to r tilde, which we computed. Okay, so now this thing here, the bracket here, the degree of gradient r squared and so on, is of course minus 2, because it's like curvature squared. So the alpha is minus 2. So we get a negative term on the right hand side. So, so we get that ddt, call this quantity g, so we get ddt of g is less, g tilde is less than Laplacian tilde of g tilde minus n times gradient of Ricci tilde squared plus n times r tilde times v tilde squared plus w tilde squared. But we just proved that this is less than a constant times e to the minus some little delta times tau. This was our previous estimate. All right, so I've thrown away the term. I don't even need this good term that I get from the alpha here, because this is negative degree. And I just brutally estimate the bad term here by our estimate, which is still on the ball above, a slightly different delta. But now I have some negative term here, and I have an exponentially decayed term. So from that I get that the whole left-hand side has to decay exponentially, maybe with a slightly worse constant. So this must now also decay. But this in particular means the first term decays. But the denominator is bounded, so this must mean that gradient r decays exponentially. With some worse constant. But it decays exponentially. So some new constant here and some smaller exponential decay rate. But you get an exponential decay. Great. Now, since the diameter is bounded, this means that the difference between R max and R min must decay exponentially. So this implies, since the diameter is already bounded by Meyer's theorem, we get that the difference between R max tilde and his tildes everywhere minus R min tilde decays like some other constant times e to the minus delta tilde t tau. Okay. But this means that in the evolution equation for the metric, the time derivative so corollary, you get that mod ddt of g tilde ij dt tau ij, which is mod of minus 2 r tilde ij plus 2 over n. And now there was little r tilde. Let me write this as capital R tilde gij. And then I made a mistake, so let's write this plus 2 over n, 2 over n r tilde g tilde ij minus 2 over n r tilde g tilde ij. Okay. Now the first part is traceless Ricci tensor, so this is bounded by V. This is less than twice V tilde. And this one here is R tilde minus small r tilde average minus r tilde. This decays exponentially because of this. So both terms decay exponentially with some. So we get that the time derivative of the metric decays exponentially. And now you proceed just like in the proof that we can extend the solution as long as the curvature is bounded, to prove that inductively that all higher derivatives also decay exponentially. And so next corollary by induction, you get that all derivatives of the Riemann tensor decay like a constant times e to the minus delta n times tau, some constant dependent. And remember, there was this condition that the metrics are all uniformly equivalent if the integral of the time derivative of the metric is finite. But since we have exponential decay, the right-hand side is finite even though the time interval is infinite. So all these metrics are uniformly equivalent, and all g tilde ij t tau are uniformly equivalent by a previous lemma. And this implies the main thing. G tilde ij of tau converges smoothly, exponentially to a smooth limit metric and on this limit metric we must have V tilde equals W tilde 0, and this proves the main theorem. And let me just remark, let me make several remarks. So, first of all, we have dealt in this case with the non-collapsing, that was the main point of this lecture, the non-collapsing using the positive curvature and the pinching and the Klingenberg lemma. Turns out, through the work of Perelman much later, we don't need to use this curvature. There is a non-collapsing theorem by Perelman which just depends on the initial data and works on any finite time interval. So, collapsing, meaning a different, meaning the lower bound on the injectivity radius can be shown much more generally on finite time intervals using a monotonicity formula. Which is related to the logarithmic Sobolev inequality. And this is the work of Perlman in 2003. So more than 20 years after Richard. We come to that later in the course. The second remark is that the second rescaling method, the second method of rescaling, where you just brutally put uses essentially the same estimate, needs the same estimate. You don't gain anything. And you lack the exponential convergence possibly in this setting. So in some sense, the result of Richard Hamilton with this rescaling the volume is nice. So third remark is, in general, rescaling by volume, the first method, which turns out to be beautiful in this case. In general, rescaling by volume is not a good idea. It's not a good idea. Because if you have a setting like this, where you expect a singularity after rescaling, looks like that, then the way you have to rescale the singularity here in order to see this cylinder will make this volume go to infinity. So if you insist on keeping the volume finite, you cannot resolve the singularity because the volume will just shrink a little bit, but you still have a huge singularity here. So just keeping the volume constant doesn't help you at all. You still get a singularity, and you still you know as much as before. The rescaling in our case only works because the whole thing contracts to length 0. And that's why the volume rescaling gives you something reasonable. For all the other more complicated singularities, just keeping the volume finite will not help at all. Okay, so that's the proof of this big pinching theorem. Now, of course, we have to find out under what conditions we can prove that the pinching condition actually holds for all time. And we will deal with that next lecture in the three-dimensional case, and then I give also some comments on the higher dimensional case. Okay, thank you.